Hello, everyone, and thank you for being here today. I am Sundus Mesudi. I'm a PhD student at Odiazic Laboratory in France, and today I'll present the work that I did with my supervisors, Sébastien Desterck and Sylvain Rousseau, about class-wise confidence for debt prediction in real estate management. First, I introduced the subject and its importance. So it is related to social housing and how it is a victim of unpaid rent. And we can see that obviously in the last few years because of COVID. So here is a little study that was done in the USA, where we see the impact of losing jobs and getting sick because of COVID-19 and how it influenced the rent pay. And so a lot of people couldn't pay anymore their rent. And so the objectives are first to anticipate tenants that are likely to fall into debt. The second one is to limit the number of tenants that can be misclassified as in debt when in fact they are not, in order to avoid paying unnecessary costs or wasting any social agent time. And the third one is we still want to recognize a reasonable amount of people who are in debt, but we don't really need to guarantee this accuracy or this error rate. So what we can use to do that is Mondrian conformal prediction. So just a little introduction about Mondrian conformal prediction and why we can use it in this case. Just a little reminder of what Henrik already said in the first talk of the first day. Conformal prediction is rigorously defined and flexible. It has prediction reasons with label sets in classification or intervals in regression. We also have a confidence measure by defining or choosing our own significance level or error rates, and we don't need any prior probabilities. In the case of Mondrian conformal prediction, we also have a validity that is verified for categories and not only global data sets. And one case where this could be very useful is the case of fair AI and, for example, this case of a machine learning algorithm that is biased in the justice system, the American justice system, where a machine learning algorithm gave harsher decisions for Black people compared to white people. And so using an MCP based on the category of race can solve this problem and have a fair or more fair machine learning algorithms. Let's see how this is done by comparing between the global or standard classical inductive conformal prediction versus Mondrian conformal prediction. So I'll take the class conditional case with the binary classification. And in the global inductive conformal prediction, we have all the examples in the calibration sets that are taken into consideration. So when we calculate the alphas for a new example n+1 by associating to it the class so 0 here and 1, we have these values, and then we compare them with all the examples in the calibration sets, and we calculate the p-value with this equation here. In the case of Mondrian conformal prediction or class conditional Mondrian conformal prediction, in this case, we actually divide the values or the examples in the calibration sets dependent on the class. So here we have for class 0 and here we have for class 1. Then when we calculate our non-conformity score for n+1, we just compare it with the examples with the same class. So we have a p-value that is calculated this way, where, as I said, we only take into consideration the examples that belong to the same class as the one we are testing for the example n+1. So here's the difference. Now we'll go to our class-wise confidence approach and why we need to use this. So our problem is we have two categories of people, or two classes. We have class 0 of people who are not in debt, and class 1 for tenants that are in debt. And so we have this equation that associates the global error rates epsilon g and the individual error rates epsilon 0 for class 0 and epsilon 1 for class 1. And we want to control the error rate of epsilon 0, so the people who are not in debt, and we also have want to guarantee a global or overall accuracy of 1 minus epsilon g. And so the first thing that we thought about is to use class conditional MCP to get this statistical guarantee and these error rates that we want to control. So what we got with our experience is this matrix, the confusion matrix here. So it's kind of a standard confusion matrix, but with just a few information that are added. And this is due to the fact that conformal predictions in the classification case for a binary classification give us three types of predictions, whether it's an empty set or a singleton or a 0-1 set prediction. And so for an empty set, this is considered as is incorrect. So we add it in these two cells here in this diagonal, and we also add its ratio. And for the 0-1 sets, they are considered as correct in both cases. So they are added in these two cells here and here. And so we also added a little information here of the singleton percentage to kind of know how much 0-1 sets are in these cells and how much singleton predictions are in these cells. And so this is a case of Mondrian conformal prediction that we tried, and that works since we have, by choosing an epsilon of 0.01, we have the 99% in both classes that are maintained and guaranteed in this case. But if we just focus on these two cells, which we will be focusing on most of the time when concentrating on this confusion matrix, and if we go back to our objectives, we can see that it doesn't work that well. Well, it still works for limiting the number of tenants that are misclassified as in debt. But if we see in this little cell here, it doesn't really work that well, because even if we have the 99% of correctly predicted tenants in debt, we still have only 5% of singleton. So 0-1 set predictions are the majority here, and for these cases, we still have we still need the intervention of an expert that will need to decide if it is a 0 or a 1. And for anticipating tenants that are likely to fall into debt, well, it kind of works. It's not really that good either, since if we go back to this cell, we still have the 99%, but with the same problem of the 0-1 sets that are predicted, and just a little bit more than the half that are singletons. We still have the same issue with this case. So that's why we thought about using our class-wise confidence by calculating epsilon 1 by choosing the epsilon global epsilon g and the epsilon 0 for tenants that are not in debt. So we, by using the equation that I showed you before, we have this calculation of epsilon 1, and we need to respect this condition in order to have a feasible epsilon 1. And so in this case, we adapt conditional MCP in order to have our statistical guarantees and our control over epsilon 0 and also epsilon g. So let's go a little bit more into details for our use case of tenants debt prediction. So the global approach was first to work with our data warehouse that was provided by the company that we worked with, which is Soprasteria. And then we extract a JSON file with the tenant's history over 2 years, 21 months approximately. And then we do a cleaning and pre-processing step to have a final data set that we can actually use for learning. And so we go to the ML and the MCP part of the global approach, where we choose the model, train it, and test it. And then the objective is to go to the prediction or the operational phase of this project in order to have the results of the tenants being in debt or not in debt. So for the extraction, as I said, we have the data warehouse that is provided by Soprasteria, where we have fact tables and dimension tables. The fact tables have more information about the tenant's account, some personal information, and the household and household details that have more information about people that live with them, or any other information about the household in general. And with this information, we also need some more details about these with related dimension tables that have, for example, more information about the rented element, whether it's a house or an apartment, where it is, how big is it, etc. Some contract details, when it started, for how long, etc. Also some household composition and income information, etc. So once this extraction is done, we still need to have some information that is added related to how we define a person that is in debt. Well, in this case, we took a definition that is in the French system, where a person is considered in debt if their cumulative debt amount is greater than 2 times their gross monthly amounts. So we calculate how much they paid each month, and we compare this with the monthly amount of times 2. So we add 2 variables each month, which are the cumulative debts and the in debts, and this being our class. Now we have this information that we have each month for 21 months, but we won't use all this history, and we just are going to consider 3 months of history. And how these 3 months are taken depends on the case of each tenant. So if we have a tenant that for all this 21 months, they were never in debt, we take just 3 random months and we take this history. But if it is a person that was in debt, then we take the 3 months that are prior to the occurrence of the debt, or we also can have another period where they were not in debt, just for comparison, and also to have more and richer data sets. And we also keep in mind that we have a latency of 1 month for each history. So more information about the cleaning. As I said, we have the history file JSON, and we also have the CSV, or the data sets, which we have each line for each example. And so here the different cleaning processes, some of them that we did are first keep the client ID or the tenant ID, and we also removed some variables that are not really useful. For example, some variables that have the same exact value for all tenants and for all examples with no history. We also have some variables without history, for example, the age that doesn't change in 3 months, or the information about the housing and where it is, and those information that don't change over time. So we keep just one value of them for the 3 months, but we still have some variables that have a history. For example, the amount of help that is provided by the French government, the amounts that are paid each month, or etc. So these are some values that change over time, and so we need to keep the history, and we have 3 columns for each month. Then we also keep the history dates. So the first date that we took for the 3 months, we keep it in a column in order to keep the history. And finally, we have our added class where we have the zeros and ones for people being in debt or not in debt. So this final data set, it has approximately 30,000 examples and 44 features, and it is strongly imbalanced and has many missing values. So now for the machine learning approach. So a summary here for all the procedure, also with the MCP or class-wise confidence approach. So we have our data sets that we split into 3 parts: proper training, calibration, and the test sets dependent on the splitting strategy. Then we take our proper training that we use in order to train our underlying algorithm, which is like GBM here, and we use it for the class predictions that we have, that we can use in order to define our non-conformity measure, is standard one here, that we used in order to have the non-conformity scores using the calibration set. Then we choose the epsilon G and the epsilon 0, or just epsilon in the case of MCP, that we use in order to set our examples and go to the test phase by calculating the p-values for each example and for each class or label. And then we can finally get our prediction region or set for our final prediction with the conformal approach. So I talked about the splitting strategies. We have 3 splitting strategies. The first one is the random one. So it's a standard or benchmark strategy where we split randomly our data set, with 20% being in the test set and 80% kept for the training and calibration. And here just a little code. Each different shape means a different person, and the blue is class 0 and red is class 1, as seen before. So as I said, we have a random splitting here. And the second strategy is a person based split, where we keep only the same person in each set. So we can't have the same person in different sets, just like here, for example, for this star, where we can have them in different sets. Here we can't. We only have the same person in the same set. And this is kind of a more reasonable splitting strategy, since we can say that in practice, the company will train on past tenants, and in the operational phase, it will have only new ones that will come later. And the last one is the time split. So this is split based on a period of time. So we choose a date here, and we took the test is based on the future, and the training and calibration are done in the past. So this is another logical splitting strategy, taking into consideration the temporal aspect. So a little spoiler here, we have the random and person strategies that worked, and for which we have satisfying results, but unfortunately for time split strategy, it didn't work that much, and we will see that more in details in the results and discussion part of this presentation. Let's go back to the underlying algorithm, which is a gradient boosting. So it shows a threshold of 0.3 since we have an imbalanced data set. And this is what we have for the confusion matrix for each splitting type. For the time, it didn't work as much since we have really bad values here. But if we go to the random and person, we have approximately the same number of people that are predicted as in that and not in that for class 1 in both cases. So we can say that the that prediction quality is almost random. Now, if we go to the splitting strategies that did work, which are random and person, and if we see the validity for by comparing the ICP or standard ICP and the class conditional MCP, we can see that the Mandarin conformal prediction gets better results and validity that is achieved not only for the overall prediction, for the overall data set, but also for the individual classes. Whereas in here, the minority class, which is class 1, suffers from validity. This is not achieved. And if we see the calibration, the confusion matrices here, okay, so for the MCP, the one that I showed you before, and for our class-wise confidence approach, and again, if we concentrate on only these two cells in each case, we have the validity, the number of misclassified not in that tenants that is very satisfying with a few examples in both cases. But if we see here again, this case, this cell, we have here, as I said, very few singletons, whereas here, even if we have just 50% that are correct, but we have a very high percentage of singletons. So if we compare the numbers, we have 108 tenants that are correctly identified here. And only 25 in this case. So here we can see the improvement that our class-wise approach gives us in this application. Now, if we go to the time that and the approach that did not really work, we can see that the validity is not really good in both ICP and MCP cases. And also, if we go to the confusion matrices in both Mandarin and class-wise approaches, we can see again that we have very, very bad results in here. Well, it's still good for just identifying one person in that is misclassified, but if we see this cell, it does not have any satisfying results with a few correctly identified people. So what now, or the conclusion and perspective for the discussion part of our presentation, where we adapted class conditional MCP in order to get a class-wise confidence, and by that we could control the error rates and also guarantee an overall accuracy. And we found that our method worked for random and person splits on real-world data, and the results were rather satisfying for our end user, which is Sopra Steria. But what's next is that we still need to work on two main problems. The first one is to investigate why the time-based split doesn't work. So we think that is related to the exchangeability assumption that is kind of violated here, and how it can possibly change the distribution or the underlying distribution of our data sets. And so we think about using some temporal distribution shifts methods. And the second problem, well, not really a problem, but it's a consideration or something that we need to do for our end user, that is still satisfied with the results, but not that much, because they want actually to control the probability of y equals c being a class, conditional to the prediction being a singleton. So, and we only provided a proxy of that. So they really are interested in this probability. So if you have any methods or any research paths that we can explore and that we can take, that would be very, very helpful. And thank you for your attention. And if you have any questions or suggestions, I will be more than happy to answer or get them. Thank you.